heat transfer example problem, natural convection for a rectangular fin array. Air flows between very thin rectangular fins with the length and height of 10 centimeters as shown. The base plate also has a width of 10 centimeters. Assume the base and fins are isothermal at a temperature of 120 degrees Celsius and that the ambient air has a temperature of 20 degrees Celsius. For part A, find the optimum spacing for the fins. For part B, find the spacing for maximum heat transfer from each fin. For part C, find the total heat transfer rate for each of the spacings from parts A and B. Our first assumption for this problem is two-dimensional steady flow of air between the fins. Our second assumption is constant properties. However, note that the density must be changing for natural convection to occur, but that we use a density at the mean temperature for our calculations. Our third assumption is that there is negligible radiation from the fin array. This is a reasonable assumption for moderate temperatures combined with significant convection. Our fourth assumption is that the fin surfaces are at a constant temperature. Our fifth assumption is that the fin thickness can be neglected in comparison to the fin spacing in our calculations. Our sixth assumption is that we can obtain reasonably accurate convection coefficients using ideal Nusselt number correlations. Our seventh assumption is that the air is an ideal gas at atmospheric pressure, which will be used to look up properties. Clearly, these are some significant assumptions, and we should only expect an accuracy of about plus or minus 20% for our results. For part A, to calculate the optimum fin spacing, we use equations to solve for this value from table 9.4 of our textbook in terms of the Rayleigh number. When we substitute the Rayleigh number into this equation, the spacing on the right cancels, thus we can solve directly for the optimal spacing. Substituting in values, we get a spacing of 0.58 centimeters. Finally, we note that all the properties have been evaluated at the film temperature of 343 Kelvin. For part B, to calculate the maximum fin spacing, we again use an equation to solve for this value from table 9.4 of our textbook. Substituting in values, we get a spacing of approximately 1 centimeter. Note that the maximum spacing corresponds to when the boundary layers that form and grow on adjacent fins just begin to interfere at the end of the channel. Also, note that for natural convection applications with air at about these temperatures, such as radiators, the fins are typically spaced about 1 centimeter apart. For part C, to calculate the heat transfer rate, we use an equation from the textbook for the average Nusselt number in terms of the heat flux for isothermal fins. Next, we substitute in an equation for the surface area of the fins that assumes negligible fin thickness. Note that to be more realistic, we could easily account for the thickness and round the number of fins to an integer, but I want to use this form to make a smooth plot of heat flux at the end of this problem. Next, we need a correlation for average Nusselt number based on fin spacing, and we again select one from the textbook where the coefficients are also given in table 9.4. Substituting in the optimum spacing from part A, we get a Rayleigh number of 936, an average Nusselt number of 1.30, and a total heat transfer rate of 2.32 watts. Substituting in the maximum spacing from part B, we get a Rayleigh number of 4,682, an average Nusselt number of 2.71, and a total heat transfer rate of 1.65 watts. Next, let us look at a summary table of our results to get a better understanding of their significance. First, note that for the maximum spacing of about 1 centimeter, we get a higher heat transfer coefficient. Second, note that for the optimal spacing of about 0.6 centimeters, we get a higher heat transfer rate of 2.32 watts. Finally, let us look at a plot of the convection coefficient and the heat transfer rate versus the fin spacing. First, note that the convection coefficient is constant above the maximum fin spacing of about 1 centimeter because it corresponds to when the boundary layers are just starting to interfere. Thus, if the spacing is larger than 1 centimeter, this convection coefficient just remains the same. As the fin spacing decreases, the boundary layers start to interfere and the convection coefficient decreases. However, a decrease in spacing also corresponds to an increase in surface area. Thus, the heat transfer continues to rise until the restriction of the flow causes the net effect to be a decrease in heat transfer. The peak in this curve corresponds to the optimum fin spacing of about 0.6 centimeters for these conditions.